that sound? Am I on? So was any? I know Glenn was in the room when I gave this talk at AGU. Were any of the others of you there? Because what happened was we had when you upload a presentation at AGU, you go to the speaker ready room. They take any format, and everything was okay. But when I went to my first slide, there were just a bunch of X's wherever an image was, and I had, I guess, Chuck, you had this happen to you too. But so this will be the first time I've given the talk in a room full of people with the images there. So that's always a bonus. But I was waving my arms so much I flew around the room. So what I'm going to talk about is an experiment that many people in this room have contributed to, stability of GNSS monumentation. How does the way you attach an antenna to the ground reflect what you're measuring? Are you measuring what the ground is doing, or are you measuring something else? So when we analyze GNSS data, what we are assuming in our models is that what the antenna is doing is really what the Earth, the solid Earth, is doing, and we need to revisit that assumption. What's the best way to accomplish that? So this has been a question that has been attempted to be answered for the 25 years that permanent GPS stations have been in existence. And do we have a laser pointer? So there have been many studies over the years that have attempted to address this station. In the middle days of Sign in Southern California, they installed 2 deep drill brace monuments next to each other. And what happened was nobody looked at the data for 10 years while one bad antenna sat there and accumulated worthless data for 10 years. Glenn and Pam did a study of monument pairs in the New Madrid seismic zone where deformation is exceedingly slow and monumentation noise is very important. But studies there were inconclusive, as when you have a monument pair, when you see relative motion, you really don't know which of the monuments are bad. In the case of this station in Hayward, near the Hayward Fault in the East Bay, which I inherited through PBO nucleus, this right here is one of the 2 very first permanent GPS stations ever installed by the USGS in 1991, a monument pair across the Hayward Fault. And we remonumented this in 2008 with a deep drill brace monument. This is in mud in the just right on the coast of San Francisco Bay. And you can see over the years the 2 time series. The red is the nice, stable, deep drill brace monument, while the blue is the wavering thing. This thing goes down about 5 feet into the mud. So you can clearly see that there's instability, relative motion between those 2 monuments, and it's easy to guess which one is moving and which one isn't. So what was done by PBO, or first of all, the motivation behind this is that most of PBO, at least 50%, were drilled with expensive deep drill brace monuments. These things are high impact. We need a water well drilling rig, and logistics are complicated. These things cost between $10,000 and $20,000. Concrete pillars, which can be installed with lighter equipment, are much cheaper at soil sites, but we really need to know, are they stable? Previous studies, as I mentioned, either had pairs or had various separations, making it impossible to tell which monument was stable or if baseline length had played a role. And there were previous studies had antenna failures, equipment swaps, And what we really need out of this is a long time series, and we had not had that from most of the previous. With this study, we made sure that also that equipment was consistent. So we're looking at 5 different monumentation types. The PBO go-to deep drill brace monument, which costs between $7,500 and takes a couple of days. And the key here is that it gets to a depth of about 10 meters, so we really anchored that as deeply as possible. And the reason PBO did this is because they could. There was Southern California network installation had the budget for this, and it's shown that those things gave good results, so PBO was funded to do that wherever possible. So the shallow drill brace, which is put in by hand, these things are only installed where there is bedrock at the surface. It's not possible to do a low-cost, low-impact monument like this with glue unless there is bedrock at the surface. An alternate style, which polar sites have used, and we used at Rio Grande Rift. Here's Dave Kasmer installing a site at Sand Dunes National Monument. A single mast can be drilled directly into solid bedrock without any lateral bracing. And this is even cheaper. A person can put it in a day, and so we wanted to look at whether the additional cost and impact of bracing a monument was worth it where bedrock is available. The pillar monuments, which I'm not sure who pioneered this. Was this Bob Smith's Utah stations, Chuck, or Yellowstone, or they predate those entirely? But this is a right. But this is one of the original monumentation styles for the earlier permanent GPS stations. So we chose five sites for three of which were existing PBO stations that, or I'm sorry, four of them were existing PBO stations that already had deep drilled monuments there. So we were adding two extra monuments for the study, and then there was one new site in Georgia where all three monuments were put in at the same time. A new PBO station was scheduled to install a new DDBM, so we also put a short drill brace monument in a map. So three of these sites have soil or unconsolidated sediments near the surface, and two of them had bedrock. So we wanted to make sure that we were selecting sites that had optimal observation, low multipath, clear sky view, and we set up triangles of monuments that were 10-meter spacing. So you can see here is a deep drill monument, short drilled. In this case, we augured and drove them to refusal using a jackhammer, and then the cement pillar, and this is in the Mojave Desert in Southern California that Chris and company installed. So what we're presenting at AGU were the first set of processed results, and in order to eliminate other site noise and isolate monumentation, we use these processing strategies. We use the standard PBO Analysis Center gamut and gypsy solutions. The uncombined solutions, New Mexico Tech does the gamut, and Central Washington does the gypsy. Henry Berglund also did independent gamut analysis using the linear combination of the L1 and L2, and then Tom Herring set up some single frequency independent solutions that remove atmospheric effects and can show short baseline movement. So what we've seen so far is that the linear combinations all show, with one exception, sub-millimeter noise for the monuments. We're but we are seeing that the pillar versus deep drill baselines are much noisier than the other driven brace monuments. We've also used kinematic epoch by epoch processing techniques to as a first cut QC and to look for other effects, and we've also identified some other interesting things that are going on. So to really get a handle on monumentation stability, you need time series over a period of years and not weeks and months as we have here. These monuments were installed during the course of the 2013 calendar year, including the last of them were installed in late September, so we really only have a few months of data. So what we see here in red is that at DELANO and California City, these are the unconsolidated sediments that the baseline estimates for the brace monuments were much smaller than the pillar. But what we have shown in red here is yet another antenna failure that polluted the results of the first few months of the Georgia analysis. So so far we're seeing that pillars appear to be as good as the sediments that you put them in. So the baseline slope estimate here, smaller is better. What you would see in a true stable environment is everything would be across zero here. So what you see is that the X's and O's show where pillars are involved, and both of those tend to be noisier than the brace monuments with respect to each other. And this also shows that vertical is, in general, noisier than horizontal, which is to be expected. At the first sediment site where we have pillars and brace monuments, everything appears to be relatively stable. We see good agreements between all monument types, whether they're pillars or braced monuments. So what we're going to do is zoom in on the last few months of this time series. So this was an existing station in the Mojave Desert. This is the history from the installation date 7.5 years ago, and the other monuments were installed here in early 2013. So what I'm going to do is zoom in on these last few months here, and this gives you an idea of the annual signal, and this annual variation primarily reflects hydrological effects, groundwater pumping, precipitation that affects the vertical signal. So what you're seeing here is not monumentation noise. This is actual movement of the antenna. And to show what we're looking at, we are in a period here of subsidence, which reflects the drought conditions in California. So what we want to see is how these things will agree over years, but right now we are zooming in on this period of subsidence over the last couple of months. So what we see here are three different colors to reflect the three different monumentation pairs. It's not really important which is which because they all agree so well, and these are Gannett linear combination solutions that shows in general at this site the three monuments are tracking each other very well, and that all three monumentation types would be equally as effective. This is the comparison of the blue linear combination results versus the independent atmosphere removed green results that show better agreement, and this is a comparison not of monumentation stability but of processing strategies, and this shows us that in the future we will get our best analysis by using, as expected, these independent single frequency analyses. And these are further detrending of the last two results, really to show that about further detail that the monuments are in very good agreement. But when we go to the other Southern California site, this is the deep drilled analysis. We can see here when we do separate analyses of the two monumentation pairs, comparing the two deep drill brace and short driven brace monuments, we see very good agreement with the green single frequency analysis. But when the pillar is involved, we see this big wobble that starts to happen last fall. And we did a lot of careful analysis here to show that this is not any other type of noise, but this is true motion of the pillar. So the pillar is sitting there wobbling with respect to the other two monuments. In Georgia, where bedrock is available at the surface, we put three new monuments in, and unfortunately at the at the mast, there was a bad antenna which sat there for a couple of months before we realized what was going on. So the agreement between the two drilled brace monuments is very good, and then once we replace the bad antenna here at the mast, we start to see very good agreement between the mast and the drilled brace monuments as well. So we are showing sub half millimeter RMS stability between the monuments and bedrock. This is a quick look at what we see. This is now an epoch by epoch solution, so it's a single day using track, which is the kinematic component of gamut hardware. This is a data QC. When you look at a daily QC of this file, it appears to be a perfect data file. But if you do kinematic analysis, what we saw was this is 10 a.m. local time every day. Our kinematic solution would be knocked out of whack and take a couple of hours to recover. And when we look at it more closely, at 10 a.m. every day, there is what appears to be an iridium satellite communications-based weather station at this local airport that caused a brief loss of lock. This does not affect a daily solution, but it does affect the ability of this station to do kinematic earthquake monitoring and real-time processing. So this was just a little offshoot of the experiment discovering unintended or unexpected results that can help in other ways. And this is an example of the failed antenna, and we've been having a spate of these at various times over the years when we've bought Trimble antennas, and how they in time series. So conclusions based on a few months of data, really the monuments are as stable as the ground that we put them in. When you have bedrock, it appears that the simplest, cheapest monument, as long as they're properly installed, is as effective as a $20,000 deep drill brace monument. Pillars, at least through this one example, do not perform well in unconsolidated sediments, but we saw one example of the two in Southern California where a pillar appeared to be fine. So what we'll be looking at is, as we look at future results, is there any way to determine whether a pillar would be appropriate for any given sedimentary location, or do you need to assume that it will not be and put a deep drilled monument? So at AGU, this was also as much an advertisement that this data set is available to the public, and I've had quite a bit of feedback that people have been analyzing these data independently of our own ACs and our own D&T staff. So that's where the experiment stands now, and we continue to monitor the data, and Tom Herring and his group have now automated the processing of these stations with single frequency as well as the regular PBO processing. So I think it's lunchtime. Questions? Since I have to answer questions for the